Now in this lecture we will talk about chemical properties of ethers, right? So when we talk about chemical properties, we mean chemical reactions, right? And in chemical reactions, first thing that we should know is the chemical structure. How does the structure of organic compound, in this case ether, right? Once you know the structure of ether, you would be able to guess around its chemical properties, right? Or the reason why it gives such types of reactions, right? So let's first look at ether. This is how an ether looks like. R, right? It has two lone pair of electrons. Right? And it is bent shaped like that of water, right? Since it has two lone pair of electrons, these lone pair of electrons can be donated to electron deficient species like a proton, right? Or some Lewis acids like aluminium chloride, boron trifluoride, right? We know these are electron deficient, which are exceptions to octet rule. If you remember, we have done this in chemical bonding, right? So what we say is, since they can donate a lone pair of electrons in chemical reactions, so ethers are Lewis bases. They act as Lewis bases, right? Ethers act as Lewis bases, right? And react with Lewis acids. Lewis acids like your hydrogen ions, proton that will come from acids, will react with aluminium chloride, will react with boron trifluoride, and then it reacts with Grignard reagents, RMGX, right? And so let's just look more into its structure. So now from this we got to know some of its important properties. Due to lone pair of electron, it acts as a Lewis base and will react with Lewis acids, right? Now if you look into its, let's take an example of any ether, say this dimethyl ether, right? This is your dimethyl ether. In this dimethyl ether, the reaction, there are different type of reactions that can take place in ethers, right? Looking at the structure, first is the reaction due to this oxygen, right? Because it can donate an electron. We call this oxygen as ethereal oxygen, right? This is an, let me write it over here, ethereal oxygen. So reaction due to ethereal oxygen, right? Second type of reaction would be reaction due to dissociation of CO bond, right? Reactions due to dissociation, or let's write reaction due to cleavage of CO bond. Now where does CO bond exists? If we look at this, if we just expand this, right? So some reactions that occur due to the dissociation of this CO bond, right? Cleavage of this CO bond. We will look into these types of reactions. Now third would be reactions due to alkyl groups, right? You have two alkyl groups, so reaction due to alkyl groups, right? So these are some important things that are easy to remember. If you know its structure, if you can remember everything. This is how it looks like, right? It has lone pair of electrons, due to which it participates in chemical reactions with Lewis acids, right? Now reactions can be of three types. Reaction due to this ethereal oxygen, where it will donate this lone pair of electrons. Second, reaction due to these alkyl groups, right, where these hydrogen atoms can be substituted by say halogens. Reaction due to the cleavage of this CO bond, right, reaction with hydrogen iodide, right. So in this lecture we will look into the first and third type of reactions, reactions due to ethereal oxygen and reaction due to alkyl groups, right. Let's first look into reaction due to alkyl groups, right. And one important thing is, if you want to compare its reactivity with those of alcohols, right, this is how an alcohol looks like, right. Now this OH group, right, and this is your ethereal group, right, this is your ethereal group. Now this ethereal group is less reactive compared to OH in alcohols, right. Why this is less reactive? If you look at the structure of alcohol, electronegativity difference exists between oxygen and hydrogen, due to which it will get minus, it will get small positive, right. Now we know we have a bond pair of electron which is between these two, which would be now shifted more towards oxygen due to its high electronegativity, right. Now since it is more towards oxygen, so it has less hold on this hydrogen, so this hydrogen can easily be lost in chemical reactions, due to which it easily participates in chemical reactions, because this proton in alcohols can easily be lost because this OH bond is polar. Whereas if we talk about this oxygen, ethereal oxygen, this is less reactive, right. But under specific conditions it does give some specific types of reactions that we will be studying now. If we talk about alkyl groups, reaction on these alkyl groups, let's say CH3, CH2O, CH3, CH2. This is your ethereal oxygen, right. This is your alpha, this is your beta carbon, this is your alpha dash, this is your beta dash. As you keep moving away from oxygen, this functional group alpha, beta, gamma, we keep doing this, right. So we have 2 alpha and 2 beta carbons in this molecule of diethyl ether, right. Now in dark, right, in dark it reacts with halogens, right. In dark it reacts with halogens and will replace hydrogen atoms, and this chlorine group will substitute hydrogen atoms, right, to form chloro derivatives, right. And so just the condition, remember the condition, in dark, right, it reacts with chlorine where it may react to form dichloro, right, this compound, right. In dark chlorine reacts with diethyl ether where substitution takes place at alkyl groups, right, since these are ethyl groups, right, at 2 sides of this ethereal oxygen. So this reaction is due to alkyl groups where substitution occurs at hydrogen atoms of alkyl groups to form these compounds. This would be alpha dash dichloro diethyl ether, right. Alpha dash means one Cl is at alpha dash carbon atom and one is at alpha carbon atom, right. That's just denoting the position. So this is your alpha dash dichlorodiethyl ether. Now this reaction is in dark, right. Now if we do the same reaction, if we do the similar reaction in complete sunlight, all these hydrogen atoms can be substituted by your chlorine atoms, right. So this would be your complete chlorination or complete halogenation, right. So when all the hydrogen atoms would be replaced, it would be CCl3, CCl2, oxygen, and again CCl3, CCl2. Right, now this is your perchloroether, right, where all the hydrogen atoms are substituted by your chlorine atoms, perchlorodiethyl ether. Right, I hope this is clear. The second reaction that we have is its combustion. Combustion is burning of ether. So ether burns in oxygen. For example, if you have C2H5O, C2H5, it burns in oxygen, right, to form carbon dioxide and water. Right, this is what normally organic compounds do. Right, and we know that ethers are volatile and highly inflammable. Right, just remember, due to this reaction is due to because ethers are volatile and highly inflammable. Right, so they burn in oxygen to give you carbon dioxide and water. So these two types of reactions are due to the alkyl groups, right? These alkyl groups present in ethers. Now let's look at the second type of reactions, or the third type when we discussed here. This first one, reaction due to ethereal oxygen. Reaction due to ethereal oxygen. Right, now when it reacts due to ethereal oxygen, here ethers are acting as Lewis bases. So it will react by donating its lone pair of electrons, as we have discussed earlier, right, to form compounds. For example, let's first look into oxonium salts, right, formation of oxonium salts. Formation of oxonium salt is that these ethers, right, will react with acids. Right, these will react with acids, say HCl, right, where we know that acid will ionize to give you hydrogen ions and chloride ions. We know hydrogen ions are deficient of oxygen. Now these hydrogen ions are deficient of oxygen. Now this ethereal oxygen, right, this ethereal oxygen that has two lone pair of electrons will react by donating its lone pair of electron to this proton, right, forming compound with it. CH3O, CH3 hydrogen, like this, right, and Cl. This is your oxonium salt. This is your oxonium salt. Due to this reaction, ethers dissolve in acids. Right? This is your concentrated acid. Similarly, you can take concentrated sulfuric acid where it forms H, and here you have HSO4 minus. Right? That is also an oxonium salt. So this is important reaction, formation of oxonium salt. This reaction takes place in cold with concentrated HCl. Right, to form this, the name of this salt would be diethyl oxonium chloride. Right, and these are stable at low temperatures and is in a strongly acidic medium. Right, they are stable at low temperatures. At high temperatures they are not stable. And if you dilute this, right, if you treat it with, or if you hydrolyze it with dilute acids, it will give you back your ether and hydrochloric acid. Right? So first thing is they are stable at low temperature, right, and due to this reaction ethers dissolve in these salts. Ethers dissolve in acids, right, to form oxonium salts. right? They are stable at low temperature. And the second thing is they dissolve in concentrated acids, right? This reaction takes place in cold, right, to form oxonium salts. And this reaction is also used to separate ether from ethyl bromide, right? Ethyl bromide that contains ether can be removed by adding HCl, where ether will dissolve in HCl, right? So which can be separated. Right, so this is an important reaction of ethers, right? Remember, this reaction is due to ethereal oxygen, where ethereal oxygen will donate its lone pair of electron to proton to form these oxonium salts, right? Similarly, other reactions with Lewis acids like boron trifluoride, right, or aluminium chloride or Grignard reagents, right, they react with these compounds to form etherates, right? And we know that ether can dissolve, Grignard reagents can dissolve in ether, right? That is why they are prepared in ethereal solutions, right? What is the reason? It is because your Grignard reagents are Lewis acids, right? They can react with these Grignard reagents, right? That is why they are soluble in Grignard reagents, right? So we'll be looking at the chemical reaction, right, that shows that Grignard reagents are always prepared in ethers, right, and are used as ethereal solution. You might have heard of ethereal solution of Grignard reagents. It's a common term that we use, right? So being Lewis bases, ether coordinates with Lewis acids. Let me just show you some examples. If we talk about C2H5, it will react with aluminium chloride, or let's say boron trichloride or boron trifluoride. Let's take commonly the compound is boron trifluoride. Let's take this boron trifluoride. We know that, if you remember our study from chemical bonding, boron trifluoride and aluminium chloride both are Lewis acid. Both are exceptions from octet rule, that the central atom boron here, it does not contain 8 electrons. Normally an atom contains 8 electrons to achieve stability, but this contains only 6 electrons. So this is short. Instead of 6 electrons, it is stable. So it can accept 2 electrons, a pair of electrons, right, from your Lewis bases. So here what will result is a coordination compound. Why? If you remember, what is a coordinate bond? Where this pair of electron is coming only from one atom. The shared pair is not from the other atom, right? Normally, like in HCl, one would be shared by hydrogen, one would be shared by chlorine. But in coordination compounds, this pair of electrons that form bonds is coming from only one of the combining atoms. So here it will go from ethereal oxygen, right, to this boron that can accept 2 electrons because it has 6 electrons, to form a coordination compound etherate, BF3. This is your compound etherate, right? We call this compound as boron trifluoride etherate, right? This is your boron trifluoride etherate, right? I hope this is clear. This is an important reaction. Now if you want to look at the other reaction, or with Grignard reagent, right, with Grignard reagent, it's like this: C2H5, C2H5, right? It will react with RMgX, right? Two molecules of diethyl ether will react with RMgX, right, to form a coordination compound, right? To form a coordination compound, these two molecules will react with it to form Rx, right? These lone pair of electrons would be through this lone pair of electron, one molecule of ether will form bond with magnesium, right? Because it can accept electrons. C2H5 twice O. The other ethereal diethyl ether, oxygen, it also forms a coordinate bond, right? Through 1,1H, through this will form coordinate bond with magnesium through one of its lone pair. This will form coordinate bond with magnesium through its one lone pair. One lone pair you can see remains, right? So this is your etherate. This is a coordination compound, etherate. Due to this reaction only, your Grignard reagents are soluble in ethers, right? And that is why they are prepared in ethers. They are prepared in ethereal solutions, right? This is an important reaction, right? So Grignard reagents, we know that these are highly unstable compounds, and these compounds, these Grignard reagents get stable in your ether, right? When you dissolve them in ether, they will get stabilized, right? This is why they are always prepared in ethers and ether solutions, right? Remember that these Grignard reagents, these compounds are unstable in solid state, right? So when you dissolve Grignard reagents in ether, you will get this compound, coordination compound. Due to the formation of this compound, these Grignard reagents dissolve in ethers and attain stability, right? So due to this reaction, just remember these, just understand what I am teaching behind this, that why Grignard reagents are soluble in ethers and how they attain stability, right? Because these things you would be using in future, right? So you should know the logic behind these things, right? So Grignard reagents are stable in ethers, right? Since they are soluble, in ethers due to the formation of etherates, right? I hope you are okay with this, right? Now let's look at one more reaction, one more important reaction, oxidation. Okay, oxidation is, this is what we have studied here was combustion earlier, right? Where diethyl ether reacted to form carbon dioxide and water, right? That was combustion, where ether was burning in oxygen. But here, if we keep ether in open air, it will get oxidized by atmospheric oxygen. We are not burning it, but it's getting oxidized by atmospheric oxygen to form peroxides, right? And these peroxides are explosives, right? So they should not be present in ethers. If you have ether normally kept in lab, right, it may come in contact with air, where it will react with atmospheric oxygen and get oxidized and will form peroxides, right? And these peroxides are explosives. They are not safe, right, for normal use. So they are checked using a ferrous sulfate solution, right? If you add ferrous sulfate solution, these peroxides will oxidize ferrous salt to ferric salts, right, which will give you red color, right? So I hope this concept is clear, right? Why peroxides are not safe, or how can you detect the presence of peroxides, right? By shaking the ethers, with freshly prepared ferrous sulfate solution, right? Followed by an addition of potassium thiocyanate. Right, so oxidation is where these will react with atmospheric oxygen to form peroxides. Like this, right? It is also bonded via coordinate bond, right? Like what we have studied earlier. So these peroxides, right? These peroxides are explosives, right? Even at low concentration, even if it is present in less quantity, it's an explosive. So the presence of this peroxide is detected by, if you have this peroxide in ether, in an old sample of ether. So what you will do is, to the ether, you will add freshly prepared ferrous sulfate, right? This contains Fe plus 2, right? It will, this peroxide, right? If it has peroxide, it will oxidize this ferrous sulfate to ferric salt, right? Followed by adding potassium thiocyanate, right? Which will give you red color, right? With potassium thiocyanate, KCNS, right? It will form ferric thiocyanate, red colored ferric thiocyanate, right? With potassium KCNS, with potassium thiocyanate, it will form FeCNS whole thrice, which is red in color. This is how the presence of peroxides are detected in old sample of ether. So these old sample of ethers must be purified before you use it, right? To get them free from these explosive peroxides, right? Simple. This is a peroxide. When you add ferrous sulfate or ferrous salt, it will oxidize this ferrous salt to ferric salt, ferrics, and then you add potassium thiocyanate. Potassium thiocyanate will react with ferric salt to give you ferric thiocyanate, which is red in color. If you get a red color, that means you have a peroxide. The presence of peroxide that must be purified, right? The ether must be purified of this peroxide before normal use, right? I hope this is clear. Thanks.